Welcome back to Lecture 11 and GRA 6036. We have been looking at a perfect residual spot, and now we'll look at a situation where one of the assumptions when we fit a model like this to the data is broken. So the assumption that we're making here is that, well, this epsilon term is 0 on average, and the variance does not depend on the value of the x. So it's the same no matter where you are on the x-axis. That's an assumption we're making when we are doing lm y tilde x and then looking at the p-values and making conclusions based on those p-values. So here the setup is exactly the same as above. We have a sample size of 100 individuals. We make our covariates uniform on -1, 1, and we set these the unknown parameters to the same values as above, and then we are to make our y's like this. But now we change change how we simulate the noise terms. So we still make them have mean 0, but we now say that the standard deviation is this. So now we see that, well, now the standard deviation is a function of the x's. So now the variance of the epsilons will depend on the value of the x. So this is noise not satisfying assumption 2. And so now we simulate these epsilons, we make our y's, and we can plot the data and also overlay the true line because we know it. And here we see that, well, now the variance of these dots, so the dots are much more spread around this true line here for small values of x than they are for big values of x. Okay, so now we'll fit. So if we fit a model, now we fit this model to these data, then okay, so let's do that, and we could add this estimated line to the plot, and we see, and from this we can learn something. So first of all, we see that the green line is very close to the blue line. So in a sense, well, the green line is the green line is a good estimate of the true unknown line. So we see that this assumption that making the variance depend on x does not really mess up our point estimates. So if we do summary of this thing, we see that these estimates are still quite close to the true values. What is messed up and what we can't no longer trust in this output is the p-values, because the constant variance assumption that is broken in these simulated data is very important for the p-values to be valid. So you can read more about that in the notes. So let's do as above and make a residual plot with these data. So that's where now. So what a residual plot will look like when we have what's called heteroscedastic data. And we plot these, and you can see the same pattern in this plot. So they are centered around 0, but their variance changes as we move along the x-axis. So here it's pretty clear from this residual plot that the assumption of constant variance does not hold. Okay, so read through the script and make sure that you understand everything that's going on, and also read the accompanying note where I explain what I'm doing in this script. And just one thing, so you can see that I have these postscript things. They are a way of, if you want, that means that I want to save this plot as this file, and then I can take this file and insert it into my document where I write my text. So then I can get, so to make a plot in R and insert it into my document like this. So when you run this script, you should comment out these postscripts parts and also these dev-off parts. So if you come here, you should comment and comment out. If not, you will not see this plot. You'll only make this file, and it will be loaded in your. It will be saved in your working directory. So when you run the script, comment them out. Okay, so good luck with project 14.